So I want you to imagine loading a 15-inch naval artillery shell into a cannon.
Okay, a big cannon.
Right. Massive. And you fire it point blank at a single sheet of delicate tissue paper.
Oh, wow.
And then you stand there and watch that massive shell just bounce backward and hit you right in the face.
Which is, I mean, a complete and utter violation of everything we consider common sense, right?
Exactly. It's completely impossible. But in 1911, that exact impossible scenario happened in a in a pitch-black laboratory in Cambridge.
Yeah.
I mean, not with naval artillery, obviously, but with subatomic particles. And it completely shattered humanity's understanding of reality. So welcome to the deep dive. Today, we are exploring the unseen interior of matter.
It's a fascinating topic.
It really is. We are going to figure out how scientists mapped the inside of an atom when it's physically impossible to actually look at one.
Yeah, and I think it's important to clarify that the impossibility there isn't just a matter of, lacking a strong enough magnifying glass.
Right.
It's a fundamental limit of physics. The wavelength of visible light is, it's thousands of times larger than the atom you're trying to resolve.
Oh, wow.
So trying to see an atom with light is like, it's like trying to feel the texture of a tiny grain of sand while wearing a giant, thick winter glove.
Oh, that's a great way to put it.
The wave just washes over the object entirely without recording its shape.
So it's not hidden the way, like, a locked space is hidden. It's hidden the way a sound is hidden from the eye, right? It's just the wrong medium.
Yeah.
And to guide us through this completely invisible landscape, we are pulling from a brilliant book. It's called Inside Matter by Boris Kriger.
Yes.
But our mission today isn't just to recite a dry timeline of physics history. We really want to understand the method itself. Like, how do you extract truth from the completely invisible?
And Boris Kriger is really the perfect thinker to frame this for us.
Yeah, tell me about him.
Well, Boris Kriger is a philosopher of interdisciplinarity. So his work focuses on how fragmented modern knowledge connects. He explores complexity and actively resists naive idealism.
Okay.
So he looks at Ernest Rutherford not just as, the physicist who discovered the nucleus, but as a pioneer of a highly specific method of inquiry.
Right.
A method that really shaped the very boundaries of what we can possibly know about reality.
Okay, so let's unpack this. Let's establish that method. Because if you have a sealed box and the rules of the universe forbid you from opening it, shining a light on it, or cutting it apart, how do you know what's inside?
Right.
Boris Kriger outlines the core technique that defines this entire field, which is basically you throw something at the box and you study what bounces back.
It sounds almost primitive when you say it out loud.
It does. It really does. I mean, it's like a person tapping a wall to find a wooden stud.
Yes, exactly.
Their knuckle is the projectile, the sound is the return signal, and from that subtle change in pitch, you infer the hidden structure behind the drywall.
Or a doctor percussing a patient's chest.
Yes. You are mapping the invisible just by bouncing energy off it. And that brings us to the actual physical setup of the famous gold foil experiment conducted by Hans Geiger and Ernest Marsden.
Right. So they needed a projectile to tap the atomic wall, essentially. And nature had conveniently provided one, which is the alpha particle.
Okay.
These are emitted naturally by radioactive elements, like radium. They're heavy, they move incredibly fast, and they carry a positive electrical charge.
So they're the bullets.
Exactly.
Yeah.
And the setup was elegantly simple. They placed a tiny amount of radium inside a lead block with a pinhole in it.
Okay.
This created a highly focused beam of these alpha particles. They fired this beam at a target, which was an ultra-thin sheet of gold leaf.
Right, the tissue paper in our analogy.
Yes. And they set up a fluorescent screen and a circle all around it to watch where the particles went after they hit the gold.
Now, context is everything here, because at the time, the prevailing theory of matter was the plum pudding model.
Oh, yes, the plum pudding.
Which is such a funny name. But physicists basically believed an atom was a diffuse, fluffy sphere of positive charge with tiny negative electrons just sprinkled throughout it.
Right, like plums in a pudding.
Exactly. So shooting a heavy, incredibly fast alpha particle through that fluffy atom should be like, I don't know, shooting a high-caliber bullet through a cloud of steam.
It should just plow straight through.
Right. Maybe drifting a tiny fraction of a degree, but nothing major.
And, I mean, if you looked at the vast majority of the data they gathered, that is exactly what happened.
Well, really?
Yeah. Most of the flashes on the screen appeared directly behind the gold foil. If you only looked at the average data, the central statistical distribution, it perfectly confirmed the plum pudding model.
Wow. But Rutherford asked Marsden to look for particles that bounce backwards,
He did.
which, according to the physics of the day, was a complete waste of time. But Marsden sat in a dark room, letting his eyes adjust for half an hour, just staring at a screen, waiting for faint flashes of light. And he found them. And that is the exact moment Rutherford made the naval shell analogy.
And that imagery perfectly captures the violence of the physics involved there.
Yeah.
Because to take a heavy alpha particle traveling at a significant fraction of the speed of light and turn it completely around, you need a single, localized, just enormous repulsive force.
Wow.
That force simply could not exist in a fluffy plum pudding model.
It just couldn't.
No, it meant that all the positive charge and almost all the mass of the atom had to be concentrated in an unimaginably tiny, dense core.
The nucleus.
The nucleus.
See, here is the detail from Boris Kriger's analysis that completely blew my mind. Only 1 in 8,000 particles bounced back.
A profoundly rare event.
Right. If they had run that data through a modern statistical smoothing algorithm, like the kind we use today to clean up noise in our data sets.
Oh, they would have completely erased the nucleus.
Exactly. They would have just smoothed it right out. The vast, overwhelming average of the data just told them the atom was empty space.
And this is a foundational thesis for Boris Kriger. Structure lives in the rare anomaly.
That's so good.
If the object you're probing is mostly empty space, the millions of projectiles that pass through cleanly tell you absolutely nothing about the architecture.
Right.
The entire foundation of modern nuclear physics was contained in an anomaly that any sensible, efficiency-driven laboratory might have discarded as just a smudge on the equipment.
A smudge. Just noise. So, okay, Rutherford finds this tiny, dense nucleus. That is an incredible triumph. But finding a fact is one thing. Making that fact fit into the known laws of the universe is a completely different nightmare.
Oh, absolutely.
Because what do you do when your groundbreaking discovery mathematically destroys physics?
You're referring to the classical impossibility of the Rutherford atom.
Yes.
It's one of the greatest paradoxes in the history of science.
Right, let's break down why it's impossible. Because if the nucleus is a tiny, massive positive dot in the center, the negative electrons have to be orbiting it, right? Like planets orbiting the sun. Because if they were stationary, the positive nucleus would just pull them straight in.
They just collapse.
Exactly. But according to Maxwell's laws of electromagnetism, which were, universally accepted, brilliantly tested, they powered the entire electrical revolution.
Right, they were rock solid.
Right. An accelerating charged particle radiates electromagnetic energy. And an orbiting electron is constantly changing direction, which means it is constantly accelerating.
Therefore, it must constantly bleed off energy in the form of light or heat.
And if it loses energy, its orbit has to shrink. So you do the math on this, and the electron should spiral into the nucleus in 10 picoseconds.
Yeah.
10 picoseconds. 100th of a billionth of a second. If Rutherford's model was accurate, all matter in the universe should instantly destroy itself in a blinding flash of light.
Which is a rather significant problem for a physicist trying to explain the stable desk he's sitting at.
Right. I mean, I'm genuinely struggling to understand how Rutherford handled this, because isn't publishing a model that you know is mechanically impossible just bad science? Like, why not throw out a plausible hypothesis for how the electrons stay up there? Propose a canceling force or some special ring structure. Why publish a broken atom?
Because that restraint showcases a remarkable, almost brutal discipline.
Really?
Yeah. Rutherford explicitly wrote in his 1911 paper that his scattering data only proved a central charge. It proved absolutely nothing about the electrons.
Oh, interesting.
The alpha particles he fired were too heavy and too fast to care about the electrons. They just blew past them.
Right.
And Boris Kriger praises Rutherford for this specific intentional refusal to guess.
He didn't want to make something up.
Exactly. Rutherford essentially quarantined the impossibility. He basically drew a line in the sand and said, the data forces me to accept this nucleus. The electrons are somebody else's problem.
Wow. He insulated his established fact from his ignorance.
Yes. And consider the alternative, because, as Boris Kriger points out, a wrong mechanism attached to right data invites the entire paper to be rejected.
Oh, I see.
If Rutherford had invented a hypothetical electron mechanism and other physicists disproved that mechanism, the scientific community would likely have thrown out the reality of the nucleus along with it.
They would have tossed the baby out with the bathwater. That is fascinating. But contrast that discipline with what happened just 2 years later, in 1913. Niels Bohr, who was a young theorist who had spent time in Rutherford's lab, he did the exact opposite.
He did.
Bohr looked at the same impossible atom and explicitly declared that electrons occupy stable, allowed orbits without any classical justification whatsoever. He just made a rule.
He essentially said, they don't radiate energy because I declared that they don't.
Right.
But we have to look at why he made that massive leap.
Okay, why?
Bohr was looking at a different set of data. He was looking at spectroscopy.
Right.
When you heat up a gas, it emits light. But it doesn't emit a smooth rainbow of colors. It emits very specific, sharp, discrete lines of color. It looks like a glowing barcode.
Ah, okay, so the colors are specific packets of energy.
Yeah, exactly. If an electron could smoothly spiral into the nucleus, it would emit a smooth rainbow of light as it fell. The barcode forced Bohr's hand. He realized electrons couldn't exist just anywhere. They had to exist on fixed, rigid steps.
Like a staircase.
Right. When an electron drops from step 3 to step 2, it emits one specific color. Bohr couldn't explain why classical physics failed between those steps, only that it failed.
Wow.
So he offered a new mathematical rule that perfectly predicted the spectral lines of hydrogen.
So Rutherford refused to guess because he had no data to support a guess. And Bohr made a massive physics-breaking guess because he did have data, the barcode, that desperately needed a mechanical home.
And both men were entirely correct in their approach.
Yeah.
As Boris Kriger argues, knowing when to declare a new rule and when to refuse to fill in the blank is the true art of science.
That's a great point. But sustaining that level of discipline, knowing when to trust the data and when to quarantine it, that requires an incredibly specific environment.
It does.
You can't just be philosophically disciplined. Your actual physical tools have to be disciplined.
Right. And it cultivated a very specific laboratory culture in Cambridge. And it was decidedly not a culture of luxury or high-tech polish.
No, it was Rutherford's string and sealing wax philosophy. He insisted on cheap, handmade apparatus, glass tubing, brass, wire, literal sealing wax.
Yes.
And the logic makes so much sense when you unpack it. Because if you build a tool yourself out of raw, basic parts, you instantly understand its failure modes.
Exactly.
But if you buy a wildly expensive, pre-assembled black box from a catalog, it can lie to you in ways you can't even detect.
Yeah, a catalog-bought vacuum tube might have a microleak that you were completely unaware of.
Right.
You might spend 6 months carefully measuring what you think is a newly discovered subatomic particle, when in reality you're just measuring ionized airborne dust slipping through a manufacturer's faulty seal.
Oh, that's brutal.
But if you seal the glass with wax yourself, you know exactly where the vulnerabilities are.
Because when you're hunting for rare anomalies, like 1 in 8,000, the danger of being lied to by your tools, or worse, by your own mind, is the greatest threat you face. Which leads to one of the most revealing moments in the book, the Vienna dispute of 1927.
Yes. We mentioned earlier that Marsden found the nucleus by sitting in a pitch-black room staring at a fluorescent screen.
Right.
Well, in the 1920s, the human retina was still the primary particle detector. Observers would sit in total darkness for 30 minutes just to adapt their eyes.
Ugh, that sounds awful.
Then they'd count faint flashes of light at the absolute threshold of human vision for a minute at a time.
It sounds like psychological torture. And sure enough, in the 1920s, a rival laboratory in Vienna started publishing results that directly contradicted Rutherford's lab in Cambridge.
Right.
Vienna claimed they were disintegrating heavy elements with alpha particles, elements that Cambridge had tested and found completely inert.
And the stakes were massive here. So Rutherford sent his trusted colleague James Chadwick to Vienna to figure out what was going wrong.
Mm-hmm.
And what Chadwick discovered wasn't malicious fraud, but a devastating flaw in human psychology.
So what did Chadwick actually do when he got there? How did he figure it out?
He sat in the dark room with the Vienna assistants. He just observed their process. And he quickly realized the fatal flaw.
Which was?
The director of the experiment was verbally announcing the experimental conditions.
Oh.
Like what target was in the machine, what the expected result was, before the assistants even looked through the microscope.
Oh, so they knew what they were supposed to see.
Precisely. Because they expected to see flashes, they hallucinated flashes.
Wow.
At the very edge of human perception, human hope was literally manufacturing phantom data.
That is wild.
So Chadwick changed the protocol. He instituted a test where the assistants didn't know what target was in the machine. He would slip in a blank target without telling them.
And what happened?
Suddenly, the impossible flashes vanished. The counts drop right back down to the Cambridge levels.
This entire episode essentially led to the birth of blind analysis, right? Where the expected answer is deliberately concealed from the human analyst so they can't unintentionally fudge the data. It's a gold standard in science today.
It is. The flaw was simply human expectation. And the ultimate solution wasn't just, training better humans. It was removing the human detector altogether.
Right.
A few years later, Hans Geiger invented the electronic Geiger-Müller counter. It did more than just count faster. It removed the human psychological variable from the equation entirely. A copper tube doesn't care what the director hopes to see.
It really doesn't. But even with perfectly objective, rigorous, data-driven copper tubes, there's another fatal weakness in this method, and that is the blindness of expertise. Deep, hard-won expertise can literally trap you inside your own assumptions.
It's a phenomenal paradox. The better you understand a system, the harder it becomes to imagine a system that operates by completely different rules.
Right. Because here's where it gets really interesting. It's 1933. Rutherford publicly states that anyone expecting a source of power from the transformation of atoms is talking moonshine. Absolute nonsense.
Right.
The very next day, Leo Szilard, a Hungarian physicist living in London, reads this moonshine quote in the Times. And he gets incredibly annoyed that an established scientist would call something definitively impossible.
Yeah.
So he goes for a walk. And while waiting at a traffic light on Southampton Row, Szilard conceives of the nuclear chain reaction.
And Boris Kriger's analysis of why Rutherford missed this is crucial.
Right, because it wasn't just arrogance, was it?
No, it wasn't arrogance on Rutherford's part at all. As an energy budget question, Rutherford was mathematically correct within his own frame of reference.
Because he was thinking about the alpha particle.
Yes. Rutherford had spent his entire life firing charged alpha particles at charged nuclei.
Yeah.
Because both are positive, they repel each other with incredible force.
Right.
The energy wasted just pushing the alpha particle close enough to hit the nucleus is enormous. You put in millions of volts of energy, and only a tiny fraction of a percent actually make contact.
It's an abysmal return on investment. You spend more energy running the machine than you ever get back from splitting the atom. So in that sense, he was right.
He was entirely right about charged particles. But Szilard was an outsider. He wasn't trapped in that charged particle paradigm. He didn't ask a physics energy budget question. He asked a structural topological question.
Okay, what do you mean by that?
He thought, what if you used a newly discovered neutral projectile? A neutron.
Right.
It has no charge, so it isn't repelled by the nucleus. It just drifts right in. And what if that collision destabilizes the nucleus so that it breaks apart and releases two neutrons?
Oh, I see. It's a loop with gain. One neutron goes in, breaks an atom, two neutrons come out. Those two break two more atoms, four neutrons come out, four make eight, eight make 16.
A geometric progression.
Right.
Szilard didn't even know which specific element would allow this yet, but he saw the structural loop.
Huh.
Rutherford's deep, unparalleled expertise in scattering charged particles made him utterly blind to a process that supplies its own neutral projectiles.
Wow. So the fundamental method of throwing things at matter is brilliant, but it relies heavily on what you're throwing and how hard you throw it.
Yes.
And over the decades, the field moved from tabletop alpha particles emitted by radium to massive particle accelerators. We started hitting matter harder and harder, and the harder you hit, the smaller the features you can resolve.
Which brings us to the ultimate limit of the throw and catch the pieces method.
Okay.
In 1968, scientists at the SLAC experiment at Stanford built a 2-mile-long linear accelerator. They fired high-energy electrons at protons to see what was inside them.
And just like Geiger and Marsden finding the nucleus, the electrons bounced back in a scattering pattern that proved the proton wasn't a solid sphere, right? It had hard, point-like objects inside it.
Quarks.
Exactly, quarks. But here is where the mechanical method entirely breaks down. Wait, really?
Yeah. With an atom, you can hit it hard enough to knock an electron off. With a nucleus, you can hit it hard enough to knock a proton out. But when scientists built bigger machines to hit the proton hard enough to knock a single quark out,
Right.
the method failed.
Wait, why? If you hit something hard enough, shouldn't it break apart? That's how everything works.
Not at the quantum level.
Yeah.
You cannot isolate a quark. This phenomenon is called confinement, and it is driven by the strong nuclear force.
Okay.
Unlike gravity or electromagnetism, which they get weaker as you pull two objects apart, the strong force holding quarks together operates differently.
Like stretching a rubber band. The further you pull the quarks apart, the more tension builds up in the space between them.
That is exactly the mechanism. If you strike a quark with immense energy and try to rip it away from its partners, the energy stored in that rubber band between them grows rapidly.
Right.
It builds up until the energy is so immense that the band snaps.
And then it flies apart.
Well, here's the bizarre part. When it snaps, all that raw elastic energy instantly converts into mass, creating brand new quarks out of the vacuum.
Out of the vacuum. Wait, so instead of getting one lonely, isolated quark, you get a spray of newly minted composite particles, which I think physicists call that a jet, right?
Yes, a jet. The harder you hit it, the more new particles you manufacture. You never get the constituent piece you were trying to isolate.
You just keep making more stuff.
Yes, you are permanently stuck. The method of breaking things to see their parts has hit a fundamental physical wall.
All right, I'm genuinely struggling to picture this. If we literally can't knock the pieces loose, how do we know what's really happening in there? Like, are quarks even parts in the way we think of car parts? If it's not just a physical energy barrier keeping them glued together, what else could it be?
And that is the ultimate question Boris Kriger poses. He introduces his own original hypothesis in the book, which he calls isotopology.
Isotopology. Okay, let's break that down.
The standard textbook explanation for confinement is what we just discussed, right? An energy barrier, where it costs infinite energy to pull them apart.
Right, the rubber band.
But Boris Kriger argues that confinement isn't just a fact about energy cost. It is a structural, topological condition of space itself.
A topological condition. Okay, let me try to translate this into a visual. It's like a winding number.
Yes.
Imagine you have a wooden pole, and you wrap a string around it 3 times, and then tie the ends together. You can slide the string up and down the pole, you can stretch it, you can wiggle it, but without cutting the string, you cannot continuously transform that 3-wrap string into one that is wrapped 2.5 times. It's a closed mathematical loop.
That analogy captures it perfectly.
Yeah.
You cannot have a fraction of a winding.
Yeah.
Boris Kriger is suggesting that the stability of the proton isn't just a lucky accident of strong forces, it's a structural necessity.
Oh.
The configuration of quarks is a closed loop. There's no isolated quark to be liberated into the universe, much like you can't have half of a Mobius strip.
Right.
If you cut a Mobius strip down the middle, you don't get 2 smaller Mobius strips. You get a new, differently twisted closed shape.
That is deeply weird, but it makes an incredible amount of sense. We're not looking at a bag of marbles we can spill on the floor. We're looking at permanent knots in the fabric of reality.
And Boris Kriger makes a final, beautiful observation based on this topological view. Think back to the alpha particle.
Okay.
The projectile Rutherford used for 30 years. 2 protons, 2 neutrons.
The ultimate subatomic bullet.
Right. Under Boris Kriger's structural reading, the alpha particle is so incredibly stable because it is one of these elementary closed configurations. It isn't just a convenient bullet that nature provided.
Right.
It is a fundamental structural brick of the nucleus itself. The larger, heavier nuclei are essentially built out of these stable alpha particle bricks.
Wait a second. So you're telling me Rutherford spent 3 decades taking the literal foundational building block of matter and throwing it at matter to figure out what matter was made of?
The probe was made of the target. It's a poetic, topological symmetry that closes the entire era of his experimental work.
That is unbelievable. I mean, this entire journey isn't just a quirk of physics history. It's a masterclass in how to interpret reality. First, you have to learn to value the rare anomaly over the smoothed average. 1 in 8,000 is your signal, not your noise.
Exactly.
Second, you must protect your established facts from your unproven theories. Know when to quarantine your ignorance, like Rutherford, and when a bold new rule is required, like Bohr. And finally, recognize that deep expertise can blind you. The energy budget expert misses the structural chain reaction that the outsider sees instantly.
Which leaves us with a critical and honestly a somewhat unsettling question about the future of discovery.
What's that?
Well, today's massive particle colliders don't have human beings sitting in dark rooms staring through microscopes. The data rates are astronomically high. Millions of collisions happen every single second.
Right. No human could possibly process that. We have to use computers.
We do. We rely entirely on automated trigger systems and complex computer simulations to instantly delete 99.9% of the collision data as uninteresting background noise. We simply don't have the hard drive space to store it all.
Wow.
But those automated trigger systems are programmed using our current theoretical frameworks.
Oh.
They only save the data that looks like something we already think is important.
Oh, wow. If structure truly lives in the 1 in 8,000 anomaly, as Boris Kriger argues, but we've programmed our machines to instantly delete anything that doesn't fit our current mathematical models, are we accidentally deleting the next nucleus? Has we built an automated system that is literally incapable of surprising us?
It's a profound dilemma. We remove the human to avoid the hallucinations of the Vienna lab, but we may have hard-coded our own theoretical biases into the silicon itself.
We started by saying the medical X-ray machine was completely useless in the subatomic world. But maybe the real danger isn't that the machine is broken. Maybe the danger is that the machine works perfectly, but it's only programmed to show us the universe we already believe is there. That is definitely something to mull over. We'll leave you with that thought. Thanks for joining us for this deep dive. Until next time.